So how do we improve this estimate? Well, one of our inherent flaws here was that we were assuming a constant rate of change, and that's going to be wrong no matter what. But I can reduce the amount of error by assuming that the rate of change is constant for a shorter period of time. But before we do that, let's take a look at the two plots. The blue plot here is the exact solution, and that is the function, comes from the function y of t equals 10e to the 0.2t. This is our approximate solution. And this is with, I'm going to write this, I'm going to say delta t, the change in time that we perceived was 1 year. We made our estimates 1 year apart. So we looked at time 0, so notice both of our points are at 0, 10. But then at time 1, we made our first estimate. Time 2, we made our second estimate. And we can also see that this error is really small at first, but it grows to be sizably larger as we move on. This is called compounding error. The reason we're compounding error is because we're using a wrong value, and with that wrong value, back here, this value was wrong, we're using that to calculate a new rate of change, which is wrong, and then we're combining those two to produce another value, which is wrong again. And then we're using wrong values and making wrong estimates with them. Now, we're not that far off, but you can see how this thing will blow up as we start to develop this for further time. One way to improve these estimates is to assume a constant rate of change for a shorter period of time. That is, we assumed our slope was constant for delta t equals 1 year. What if we updated our slope every half a year? Well, if we did that, we have to be a little bit cautious because remember that dy dt, as we said earlier, is per 1 unit of time. So this is still 2 elk per 1 year. But notice that the time advance here, the time step, or the step size as we call this, is half a year. So if this is a ratio of 2 elk per 1 year, my change in y is not actually going to be 2. My change in y is going to be my step size, which is half a year, and I'm going to multiply that by f of ty. Now remember, another way of saying this is just, this is dy dt, but the reason I write it as f of t comma y is because it allows me to actually specify the t and the y that I'm positioned at. So here I'm looking at f of 0 comma 10, and in other words that equals half a year times 2 elk per year, right? So if I only change time by half a year at a rate of 2 elk per 1 year, then that comes out to 1 elk. That's my change in y. Notice that the years are gone now because the years cancel out, and I'm now left with just a gain of a change in y of 1 elk. So instead of now taking 10 plus 2, I'll only do 10 plus 1, which equals 11. Again, that's only half the time, so I should only gain half the elk. Now I'm going to repeat the same process. I'm going to calculate 20% of, but now it's going to be 11. That's going to be 2.2 elk per 1 year. Again, that's 2.2 over 1. So to calculate the new slope, what I have to do is take my time step, which is half a year. By the way, these time steps shouldn't ever change abruptly. You should settle on a time step and stick with it all the way through. Otherwise, you get weird compounding of errors. Now that's half a year at 2.2 elk per 1 year. So my change in elk will be 1.1 elk. Again, my years cancel out. Beautiful dimensional analysis here. So I expect to change y by 1.1 elk. We're at 11, so we're going to add 1.1 to it. That's going to give us 12.1 elk at time 1. And you can already see that our estimate here is 12.1 elk at time 1, whereas when we did 1 year at a time, our estimate was 12 elk. The actual answer at time 1 is 12.21 elk. So you already see that our estimate at time 1 is a little bit more precise. Now, of course, I'm going to repeat this process. I'm going to repeat this process many times. So rather than to continue writing this out, I hope that you get the sense of what's going on here, but continue to work this out. What we should get is 13.31, 14.64, 16.1, and so on. And at time 4, we get an estimate of 21.44. So the key here is whatever your step size is, that's the factor by which you need to scale your slope so that you get the number of elk that you're expected to gain just over that shorter window of time. So if this was 1/10 of a year and we went 0, 0.1, then this would be 1/10 of a year change times 2 elk per 1 year, and that would mean we would only expect to gain 0.2 elk. All right, so I encourage you to fill out this table, verify this. But here are the 3 graphs once again, and you can see that on top we have the exact solution. So this one is the exact, and that once again was y of t equals 10e to the 0.2t. Down here we had the estimate for delta t equals 1/2 a year, and I'm sorry, for delta t equals 1 year. And you can see that the little x's occur, our new estimates occur every 1 full year. The purple curve here, you can see that there's still straight line segments, but every time 1/2 a year passes, we get a brand new estimate. So this purple point here is an estimate for a 1/2 marker, whereas in the green graph, we did not estimate that. So let me find my closest to a purple. There we go. This is purple. So this is estimate for delta t equals 0.5 years. So you can see that the tightness of our error is getting better. So we have a lesser error here. Still, that error is growing, so that should be alarming to us. It's still getting bigger as time passes, but it's not quite as big as, for example, here we saw that this error was much larger. I'm just putting that a little to the left so you can see the distinguishing lines. You can see that we've about cut the error in half, if not a little more. So clearly there's a direct trade-off between the step size, so that's the name of this delta t, and the precision of the estimates. As we make delta t smaller, we get closer to the exact answer, as evidenced by the spacing between our exact curve and our estimated curve. But on the other hand, as we make delta t smaller, we increase the number of computations, right? We had to double the number of computations in order to cut the time step in half. We had to basically make our table a lot larger. We had 1, 2, 3, 4, 5, 6, 7, 8 time steps, whereas here we only had 1, 2, 3, 4 time steps. So we gain precision, but we increase the number of computations. For Euler, back in time, I'm not going to give you an exact year because I don't know exactly, but there were not computational devices that were efficient enough to sort of break up this trade-off. Now with computers, and computers being as fast as they are, making the time step really, really small does not add too much load on a computer. But that being said, if you make this time step really, really small, like 0.00000001 or 1 times 10 to the negative 20th, it's going to put a strain on any computer. So let's think about, before we actually allow technology to take over for us, let's think about what this process looks like. So if we were computer programmers, we would know what we need. Well, we need a differential equation, something that gives us the rate of change, because that's what we needed in order to make time steps. We needed some initial condition. I didn't say initial here because we don't have to start at time 0. We could start at time 5. By the way, if you start at a different time other than 0, that's called a boundary value problem instead of initial value problem. The next thing we did is we calculated the change in y. For a time step of 1, remember delta t was 1, so all we had to do was calculate the slope. But if our time step is half, then we need to scale the change per 1 unit time by whatever our change in time is. And then now we calculate the new y value. So visually speaking, that the y value of that next ordered pair, we got that 14.4 by taking the current y and adding the change in y to it. And then we also had to increment time by its time step. So those two processes are described here in steps 3 and 4. So the next y value is the previous y value plus the change in the y. The new t value is the current t value plus the change in the time. So now we have the ordered pair. We put these two values together. We have that new ordered pair that we can now graph. We repeat this cycle from steps 2 through 5. We loop this enough times to get to our final ordered pair. Whatever our stopping point in time is, we continue doing this. So these steps 3 and 4 can be thought of more generally as to get the next time, a next t value. So t of k plus 1, that just means 1 time unit later. It doesn't have to be plus 1 year. It could be just t1 could be half a time unit later. So we're going to take the most recent value of time, increase it by delta t. So for example, if right now we're at time 0 and our time step is a half, so if this is right here is t0 and I want the next time step, 0 plus a half will give me 0.5. So back here in our table, we could think of this as being t0, t1, t2, t3, t4, t5, t6, t7, t8, and this is y0, y1, y2, y3, y4, y5, y6, y7, y8, and so on. So notice that these subscripts do not actually denote what value the time is, it just denotes the current time step. And delta y, recall, is given by calculating the slope, the rate of change per 1 unit time, and then scaling it by whatever our change in time is.